In the last video, I talked about the extremal types theorem, which is this one, and it said that there are three possible limits if the limit exists. Now the question is, how do you know which of them is going to be attained, if at all one of them is attained, right? So the answer for that question will be given in this video, right? So here we go. So the question, the question is the following: how to know which of the three limits is attained, if there is a limit. So this is the question, and I'm going to give the answer to the question in a sec, so just bear with me. So the answer is as follows: type 1, or the Gumbel type, so type 1, or the Gumbel type, will be attained if the following condition holds. So the condition is that I will explain what W of f in a minute. So first let me write down the conditions, then I will explain what this means. Type 2, which is the fresher type, will be attained if So type 2 will be attained if W of f is infinity and the limit of this is equal to x power minus alpha, where alpha must be a positive real number, right? And type 3, which is the Weibel type, All right, so the type 3 will be attained if w of f is finite, finds a finite number, and the limit of this as t approaches 0 is equal to x power alpha, where once again alpha must be a positive or real number. So these are the three conditions so this is the condition for Gumbel or type 1, this is the condition for Fresher or type 2, and this is the condition for Weibull or type 3. Now, one thing I must say is that only only one of these three conditions will ever be satisfied. So if this condition is satisfied, these two will not be satisfied, and if this condition is satisfied, these two will not be satisfied, and finally if this condition is satisfied, then neither of these two will be satisfied. So only one of them will be ever satisfied. All right, now next thing, before I go ahead, I like to talk about w of f, which I have not defined. So let me define what I meant by w of f. So let me take this away. So here I will talk about definition, of w of f. So w of f, loosely speaking, it is defined as the following: is the upper endpoint of the support of f, right? Formally speaking, w of f is defined as the supremum of the set of all x's for which f of x, the CDF, is strictly less than 1. So this is the formal definition of w of f, but this is the loose definition of w of f. But you don't need to worry about taking the supremum. So easy way, sorry, excuse me guys, an easy way to find w of f, right, is to set f of x equal to 1. So this is f of x equal to 1, and then solve for x, right? This is the easy way to find the w of f, is to set the CDF equal to 1, and then whatever the solution that you get for x out of this is w of f. So let me give you a couple of examples. So example 1, Now suppose your f of x is equal to this, which is the, I'm sure you know that this is the CDF of the exponential distribution. Now if you set this to equal to 1 and solve for x, let's see what we get. So this means that e of minus x is 0. So this, you should take the log, so you get minus x is equal to minus infinity, right? So x is equal to plus infinity. So therefore w of f is equal to plus infinity. So this is example 1. And example 2, let's take f of x to be equal to 1 minus 1 over x, right? And this is a Pareto type distribution. To find the w of f, we need to set this to 1 and solve for x, right? So this implies that one over x is equal to 0. So this implies that x must be equal to plus infinity, and therefore w of f must be equal to plus infinity, right? So in both these examples, w of f is equal to infinity. A third example, if I have time, is let's do a third example. So here f of x equal to x, which is the uniform distribution. All right. Now to find the w of f, we set x equal to 1. All right. So therefore, which implies that w of f must be 1, right? In this case, right. So these are 3 examples on how to find w of f. Okay. Right. The next thing I'm going to do is to go back to the conditions. So these are the conditions I gave you, and I'm going to do a few examples on how to check these 3 conditions. Right. Okay. So the first example. So these are, let me say, examples on checking conditions 1 to 3. Okay. So let's look at first example 1. Let's take the CDF to be the CDF of the exponential distribution. Now the question is, which of the 3 conditions is satisfied? Right? We know from the previous slide that w of f must be equal to plus infinity. Right? So let's start by checking condition 1. The condition 1, for condition 1, we are looking at the limit as t approaches w of f of 1 minus f t plus x gamma t divided by 1 minus f ft, right? And this is equal to the limit as t goes to infinity, because we know w of f is infinity, of 1 minus, we know what the CDF of is, we know what f is, and this is what you get. Now the 1 and the 1 cancels. Okay, so what you have is the limit as t goes to infinity of right, and this becomes the limit as t goes to infinity of and this is equal to e of minus x if we take gamma of t to be equal to 1. Alright, so hence condition 1 is satisfied. Remember that for the condition 1 to be satisfied, the limit must be equal to e of minus x, right? So the conclusion is the following, that hence such that the limiting distribution of star, which is right. So this is the conclusion. So we have shown that the Gumbel type is attained. So in other words, there exist constants an and bn. An is positive, bn any real number, such that the limiting distribution of this, which I called star earlier, must be equal to the Gumbel distribution as n goes to infinity. Alright, so this is the first example. The second example I'm going to look at is the following. Alright, this is, so suppose f of x equal to 1 minus 1 divided by x, and we saw earlier in the example that we did earlier, we saw that w of f for this is plus infinity. So let's check condition 1 to start with. So this is the limit, and this must be equal to equal to this, and once again the ones cancel. Okay. So what you have is the limit as t goes to infinity of t divided by t plus x gamma t. And for condition 1 to be satisfied, this limit must be equal to e of minus x. And there is no chance that the limit of this can be equal to this. So hence they can never be equal. But hence condition 1 fails to hold. Right? So that means we need to check condition 2. Right? So let's see if condition 2 holds or not. Okay. So the condition 2 says the following. Condition 2 says that you're looking at the limit as t approaches infinity of 1 minus ftx divided by 1 minus f at t. Right, so this is the limit as t approaches infinity of this. Yeah. Now once again the ones cancel. So what you have is the limit as t approaches infinity of 1 divided by tx divided by 1 divided by t, and this is clearly equal to 1 over x. Right, and this is the same as x to the power minus alpha when alpha is equal to 1. Okay, so hence condition 2 is satisfied. Right, okay, hence All right, so the conclusion here is that because condition 2 holds, there exists an positive, Bn a real number, such that the limit of star is equal to the Fréchet distribution with alpha equal to 1. The next example is example 3. So here I'm going to suppose that f of x is equal to x for x between 0 and 1, right? And this is the, as you know, this is the CDF of the uniform distribution on the interval from 0 to 1. Okay, now we know from earlier that W of f for this distribution is equal to 1. So let's start checking the three conditions, starting with condition 1. So I'm checking condition 1, and this is equal to the limit as t goes to 1 of and this can be written as the limit as t goes to 1 of 1 minus x gamma t divided by 1 minus t. And for condition 1 to be satisfied, this must be equal to e minus x, and there is no chance that the limit of this can be equal to this. So hence condition 1 fails to hold. Okay, now let's check condition 2. Condition 2, one of the requirements for condition 2 is that the W of f must be infinity. But in this case, W of s equal to 1, which is not equal to infinity. Right? It's a finite number, right? So hence, condition 2 also fails to hold. Okay, so let's now check the last condition, which is the condition 3. All right, so right, and the ones cancel out, the 1 and the 1 cancel out. Okay, so what you have is the limit as t approaches 0 of tx divided by t, and which is equal to x. and this you can write as x to the power alpha with alpha equal to 1. Alright, so hence condition 3 is satisfied. Okay, so the conclusion is that condition 3 holds with alpha equal to 1. Right, so hence, according to the extremal types theorem, there exists such that the limit of star, which is this one, approaches the viable limit, which is e, when alpha equal to 1, it becomes e of minus minus x, which is x, right? If x is less than 0, and is 1 if x is greater than or equal to 0, right, as n goes to infinity. Okay guys, so this is example 3. Now the next topic I'm going to cover is about alternative conditions for, remember that at the beginning of this video I gave you three conditions to check. So this is the condition if the type 1 limit will be attained, and this is the condition if type 2 limit will be attained, and this is the condition for type 3 limit, right? Now these three conditions all involve capital F, which is the CDF of the data. Now sometimes it's more convenient to work with the little f, which is the density of the data. So the conditions I'm going to give you in the next video will mainly involve little f, which is the derivative of capital F, or the density of the data.